Hello, ladies and gentlemen. It's evening. Hello, ladies and gentlemen. It's evening here. I usually like to do my recordings in the morning. This lecture will be covering sections 1.2 to 1.4 of our text. Here's the text. You can barely see it because I'm using a virtual background, but I won't even try. Okay, so we're going to get started. I have to pull up the whiteboard or the blackboard, depending upon your point of view. For me, it's black, and that's what took me so long to record with because I had to download some firmware to get this to work for some reason. Okay, so here we go. Okay, so let's start now with 1.2, which is about counting. And what are we counting? Well, we want to sort of compute the number of ways of arranging things or the number of possible outcomes of performing a sequence of experiments. Let's talk about experiments. Suppose I have two experiments. Let's call the first experiment E subscript 1 and the second one E2. And E1 has n outcomes and E2 has m outcomes. So what are the number of possible total outcomes of performing both experiments? Well, for each time we perform E1, there are m possibilities for outcomes for E2. So there's going to be, you see that it's got to be a product. It's got to be n times m. So that's the basic rule, but we can generalize this. So we can generalize this to uh, uh, say K experiments. E1, E2. I'm thinking of the outcomes as fitting into a little basket here, E3, all the way up to EK. And E1, let's say there are N1 sub 1 possible outcomes, E2 has N sub 2 possible outcomes, E3 N sub 3, all the way up to N sub K. So the number of outcomes, total outcomes of all the experiments is going to be N1 times N2 all the way up to n sub k. And I'm sure many of you have already seen this in your previous math classes. So that's the basic counting rule, or the product rule for counting, you might want to call it. So let's do like an example. So this is from the text, seven entry license plates. How many are there? The convention will be that a license plate consists of uh, three letters followed by four numbers from 0 through 9. So let's think of this as given by 7 experiments where you have letter, letter, letter possibilities, and then number, 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 number. So how many outcomes are there? Well, there are 26 possible letters because the letters of the alphabet, there are 26 of them. So it's 26 times 26 times 26, which I'll write as 26 cubed times, well, there are 10 numbers from 0 through 9, so 10 to the 4th power. So that makes, I guess, if you calculate this, 175 million, I didn't do this in my head, 760,000 possible license plates. Okay, let's do another example, also from the text. Let's enumerate the number of functions from the set 1 through n to the set 0, 1. So we're going to look at functions. A function is a rule which assigns to every member of the domain, in this case the domain is the set 1 through n, an element in what is called the codomain, or 0, 1. So every number here from 1 to n has to be assigned a 0 or a 1. We can think of this as n experiments. say where experiment 1, experiment 2, all the way up to experiment n, dot, dot, dot. And experiment 1 has two outcomes, 0 or 1. That's what you assign to the number 1. And then experiment 2 has two outcomes. Experiment 3, all the way up to experiment n, it has, you're going to get 2 to the n possible functions or outcomes. So that's the answer for that problem. We can generalize the previous example as follows. Suppose we look at functions f from 1 through n, but now we don't go to a set with 2 elements, we go to a set with m elements, say 1 through m. I'm using different notation here because there's no 0 in the set 1 through m, but it's the same idea. So you got, again, n experiments, but the first experiment and every experiment has m outcomes, so it's m times m times m. So it's m to the nth power. That's the answer to that example. Okay. Okay. Let's continue then. There's one other variant of number of this example number 3, number 3. Suppose we look at license plates. And we don't allow repetitions of the letters, no repetitions of the letters or the numbers. So, like, it's still 7 experiments we're performing, 1, 2, 3, 4, 5, 6, 7. But the first experiment, how many choices are there? There are still 26 choices of the letters. But now once you've chosen that letter in the first slot, there are 25 choices for the remaining letters you can actually put in slot number 2. And then there are 24 letters left for slot number 3. And then as far as numbers go, you have 10 choices for the first slotted number, then 9, 8, 7. So that's what it is. It's 26 times 25 times 24 times 10 times 9 times 8 times 7. And this turns out to be 78,624,000, which is roughly, it's actually less than a half of the number of the example that occurs in number 3 above. Okay, so those are some examples. Okay, so we are now done with section 1.2. So let us move over to section 1.3. Let me clear the screen or the board. Okay, so what's 1.3 about? That's called permutations. So what is that? Well, let's just do by example again. Suppose I have, like, I don't know, the first 4 letters of the alphabet, A, B, well, the first 3 letters of the alphabet, right? How many ways can I arrange those 3 letters, right? Well, I could arrange them A, B, C, or B, A, C, or B, C, A, etc. And we want to know how many possible ways of arranging them are there. Well, you can think of this as performing 3 experiments, one for each letter. No, well, 3 experiments. In the first experiment, we choose a letter, say A or B or C. There are 3 choices. And now in the second slot, there are not 3 choices. We've used up a letter. So we have to put one of the remaining letters, and there are 2 of those, and then there's 1 remaining for the third slot. So it's 3 times 2 times 1 is the answer, which is equal to 6. And in fact, we have the notation of n factorial, which is 1 times 2 times 3 times 4 all the way up to n. And so really the answer was 3 factorial. 3 factorial is 6. Okay, so that's the answer for that. Okay, So in fact, what does n factorial solve? N factorial is the number of ways of arranging n items. That's what it is. So for example, let's do an example. 10 workers are assigned to 10 different jobs, one job per worker. How many possibilities? How many possibilities? How many arrangements are there? Well, we can think of performing 10 experiments. So you have the first worker, there are 10 choices of jobs he or she can take. But then with the second worker, there are only 9 jobs left. And with the third worker, 8 jobs, all the way up to, goes down to 1. So it's 10 factorial is the answer. So, you can compute 10 factorial on your calculator, or you can use a web-based calculator to compute 10 factorial. I can actually pull one up. Well, I won't pull one up. You can compute it yourself, but well, maybe I will. Let me pull one up. 1 second. So I actually use Google. Google has its built-in calculator. We can compute factorials with it. And I just put in 10 factorial and I get 3,628,800 for the answer. So you can just do it with Google. But when we do more complicated things, we have to use some other URL to do that. Okay, so um, going back to business here, um, these problems get harder. So let's do an example again from the text. So the problem is, so this is example 3D in the text, 3D in section 1.3. And the idea is to take the word pepper, and how many ways of rearranging the letters are there in pepper? Now, the P's are all considered the same letter in this word as are the E's. So if I were to permute the two E's, that doesn't change the arrangement at all. Or if I switch the P's around, it doesn't change the word. So we have to take that into account. And so the solution, so how many arrangements of pepper are there, is to do the following. We label each P with a different subscript. So P and each E, E1, P2, P3, E2, and there's only one R, so we don't have to put a subscript next to that, right? Now, if we think of these now P's as all different, and the E's is all different, the two E's is different, how many ways are there of rearranging these symbols are there? Well, there are 1, 2, 3, 4, 5, 6 symbols, and the set of ways of arranging 6 symbols is 6 factorial ways, right? But some of these ways do not do anything for the original word pepper. For example, if I were to switch P2 and P1 and do nothing else, from the point of view of the original word pepper, the original set of symbols, nothing has changed. So we have to take that into account. And so how many ways of doing the switches with the P's are there? So if we switch around all the P's without changing the arrangement of the between the P's and the E's and the R, there are exactly 3 factorial ways, because there are 3 P's, of arranging the P's. And there are 2 factorial ways of arranging the E's. So, and there's 1 factorial, but 1 factorial is one way of arranging the R, so of permuting the R's. So what we have to do is we have to take the 6 factorial. the set of all these arrangements and group together the arrangements which don't change the original word. And we know that there are 3 factorial ways of arranging the p's and 2 factorial ways of arranging the e's. So if we take that all together, there are 3 factorial times 2 factorial ways of arranging the p's and the e's, all of them. And so we have to identify those various arrangements, and the way you identify is by dividing out by them. So it's 3 factorial times 2 factorial. That's the answer to this problem, and it turns out you can compute this. It's because you can think of this as 6 times 5 times 4. The 3 times 2 times 1 is killed by the denominator of 3 factorial divided by 2 times 1, so that turns out to be, it looks like 60. Okay, there's 60 ways of rearranging the letters of pepper. Actually, this last example, it gives you the principle. So this might be called number 3. The principle that we've just sort of noticed is this. Suppose we have n objects. So in this case, we have 3 objects, P, E, and R, and there are n1 of the first kind. So we have 3 P's and n2 of the second kind. Etc. And we have nr of the rth kind. So in this example, we have and here the n1 plus n2 all the way up to n sub r. They have to add up to n. Okay, so here r is actually 3. Because there's P and there's E and there's R, right? There are 3 P's, there are 2 E's, and there's 1 R. R is 3. So it's a different kind. There are kinds of objects. R kinds. Okay, and then the answer is the number of arrangements. Oops, I have to erase. Number of possible arrangements is given by the following expression: n factorial over n1 factorial times n2 factorial all the way up to n sub r factorial. It's the same sort of reasoning which gave the previous example. So this is called a multinomial coefficient. We'll see why that term that's called that later, but this is usually given notation. It's n, and then we have an n1 comma n2 all the way up to nr, and so we usually write this expression like this. By the way, when I put 2 dots next to an equal sign, that means that's the definition of it. So that's called a multinomial coefficient, and we've computed, in the previous example, we actually computed a multinomial coefficient. It was, we have 6, and then there were 6 objects, P, E, P, P, E, R, and then there were 3 of the first kind, 2 of the second kind, and 1 of the last kind. And we saw that that is given by 60. Okay, so that's the example. So what I'd like to do next is an exercise out of the text. So I probably should pull up the text for this. So let me do that now. So what I'd like to do is discuss the following problem. Where is it? It is problem number 11. Where is it? On this page of the text. This is actually an older version of the text, but it is called problem number 11, and it's on page 16 of the text, right? So this is an older edition of the book, and you see it's on a different page. So, in how many ways can 3 novels, 2 mathematics books, and 1 chemistry book be arranged on a bookshelf if A, the books can be arranged in any order, B, the mathematics books must be together and the novels must be together, or C, the novels must be together but the other books can be arranged in any order. So this is something that requires thinking about what the question is asking. Okay, so let's go back to the whiteboard and let me clear the board and let's discuss the problem. Okay, so this is exercise number 11, not example, but exercise, page 16 in the text. Okay, so there are 3 novels, 2 math texts, and 1 chemistry text. And we are supposed to consider all possible ways of arranging them. If A, the books are allowed to be arranged in any order. Well, um, that shouldn't be too difficult to solve because we have 3 books. We have 6 books, 3 plus 2 plus 1. And we're allowed to arrange the books in any order on the shelf. So it's 6 items and we're allowed to arrange them in any way. So it should be 6 factorial, should be the answer in that case. In B, we are requiring that the math books are together and that the novels together. So you cannot separate them on the shelf. So if a math book goes, say, in slot number 3, a math book must either be in slot number 2 or in slot number 4. They have to be touching each other. Okay, so how do we do that? Well, let's sort of group the math texts and the novels together in some ways. Let N denote the set of novels, M denote the set of math books, and then we have chemistry. Now on the shelf, so in other words, on the shelf, we would have 2 together under the label M, and then we'd have 3 novels under the label N, and that's how many ways of these arrangements are there? Well, there are 3 different kinds of books in the way we've set this up. So there are 6 factorial arrangements. I'm sorry, 3 factorial arrangements of these items, but if we go to each item, we have, in the case of novels, there are 3 novels, and there are 3 factorial ways on the shelf of arranging 3 novels, and there are 2 factorial ways of arranging 2 math books, and then there's 1 way of arranging a chemistry book. So it's not just 3 factorial arrangements because we can we can look at all the permutations of the 3 novels and all the permutations of the 3 math books, and that's going to multiply. So it's going to be 3 factorial times 2 factorial for each such arrangement NMC. And when I say there are 6 arrangements, because you could put the math books first, and then the novels second, or the math books third, the novels second, and so on. Okay, so the final answer to this part B is this expression here. And then in part C, what do we got? Well, we're asking about the novels being together, but no other restriction. So how do we do that? Well, what we have is, if we're sticking the novels together, let me put N as the set of all novels, And then there are no other restrictions in the remaining categories, right? So how many remaining categories are there? Well, we put the three novels together. There are three of them. And how many texts are left over? There are three texts left over. There are two math texts and one chem text. And these can be, so we have four things we can permute. Uh, and it's going to be 4 factorial. But now we have the additional permutations of the novels that can occur within their own categories. So there are 3 factorial of those times the 4 factorial. So that's the answer to part C, 3 factorial times 4 factorial. Okay. So this takes care of at least the lecture portion of section 1.3. I now move on to section 1.4, so let me clear the screen. Okay, so 1.4, oops, 1.4 is entitled Combinations. And again, many of you have probably seen this topic elsewhere. For example, if you took 2000 level of probability and statistics, you would have learned some of this. So how many ways, so here's an example of a combination question. How many ways can I select 2 items from a set of, say, 4 items? Okay, so where I don't care about the order of the items I select, I take them out at the same time, in other words, right? So that's the question. So for example, suppose my items are the 4 letters of the alphabet, and I want to select 2 of these items. Well, that means A, B, I could be selecting, and that's a set. A, B. A, B, and B, A are considered the same, right? It's not an ordered pair, it's just a set. And then B, C, we have, and then we have AD, etc. So how many ways to do that are there, right? I can actually work it out. AB, AC, AD, BC, BD, and then we have CD. And that's all the possibilities of choosing 2 things from 4 things. So there are 6 possibilities, 6 possible ways. So how can I make sense of this calculation? Well, suppose instead of calculating the ways I select 2 items in an unordered way from 4 things, suppose I consider the corresponding ordered question. I select 2 items in order. So that would be like performing an experiment. There's a first item and a second item, right? So how many ways are there to choose the first item from the set of 4 items? Well, there are 4 ways. And then how many ways are there to choose the second item? There are 3 ways. But now I'm allowed to consider, there's no first item and no second item if I don't consider order. So AB is the same as BA. So I have to equate AB with BA, and they're each way of selecting these 12 items is paired off with a unique other way by permuting the 2 items. So it's given by, the answer is that you got 12 from this, but then you have to divide this by 2 factorial, the number of ways of permuting 2 things. So 12 over 2 is 6. So that's how to understand this. So more generally, the principle is this. If I have k items and I selected from n items, and the order of the k items does not matter, then the answer is I would get n times n minus 1 times n minus 2. So the first, suppose I ordered them, I would n minus 1, n minus 2, all the way up to n minus k plus 1. That's the way of selecting k items in order. But now I have to divide by the ways of ordering k items. Well, that's k factorial. So this answers the question of how many ways of selecting things in order, but then I divide out by the number of orders. So this is called n choose k, or the symbol is given by this. It's n choose, this is what you actually call it, n choose k. That's how you say it. So you're choosing k things from n things. And there's an easier way to remember the right-hand side by rewriting it. This is n factorial over k factorial times n minus k factorial. And if you like, this is can be rewritten as a binomial coefficient, k comma n minus k, where we go back to one of the previous slides, whiteboard slides. So n choose k is the same as n k comma n minus k. So n choose k. So this is what a combination is. So I think I'll just end this lecture for now with just a single example, and we'll do some more examples next time. So suppose I consider a deck of 52 cards, standard cards. So, and how many ways can I deal out a 5-card hand? The number of 5-card hands. So when you deal out a hand, it doesn't matter the order of the cards. It just matters that you get the 5 cards, which 5 cards you have, but the order in which they're dealt to you does not matter. And so that's going to be a combination. And what combination? Well, there are 52 things, and I'm choosing 5 from the 52. And the answer is 52, choose 5. Now, in order to compute what that actually is, you should use your calculator if you wanted to get an exact expression for it. You can use your calculator, or you can use an online combinations calculator. So let me show you one. Let me see if I can find one here. Okay, so here's one. So I put it in. This is called Calculator Soup, calculatorsoup.com, but there are lots of them online. So the number of objects is 52, and R, which I'm calling K, is 5. So I calculate, and I get the solution, and it's 259,000, no, 2,598,960. Okay, so let's go back to our whiteboard. Okay, so this is 598,960 possibilities for a 5-card hand. And I think that is going to be it for today, or this evening. I'll be posting more lectures, probably 2 more this week. And so you'll have more to look at. And I'm also going to post my lecture notes, the notes I lectured from today. And I hope this is not incredibly boring. If it starts getting more boring, I might have to tell some stories. Okay, so have a good night.